All right. So, okay. So, so if your WP, just a minute. Okay. So if your WP, the length of the P side is much higher than the minority carrier diffusion length, right? So if WP is more than Ln, so these excess minority carriers will be recombined, right? So in the steady state, so delta NP at minus WP, that the edge of this P side or very deep into the P side, it will be 0, right? And similarly, I could also write the excess holes in the n side, delta P n x n dash is Ni square by Nd times e to the cube here by Kt minus 1, and delta P n Wn equal to 0, right? So these are the conditions I could write down, right? Because the holes will be injected, and the excess minority holes in the n side, right? Excess holes, minority carriers, right? In the n side will be Ni square by Nd times e to the power cube here Kt by Kt minus 1, right? Okay. So so now means basically if you means we'll see that, right? So basically these minority carriers will go to 0, so I could draw it like this, right? So I have to solve the continuity equation to get the distribution, how the delta NP is distributed in the P side and how delta Pn is distributed in the N side, right? Okay. So however, in the depletion region, right? So but your depletion region is much less than your Ln and Lp, right? Because if you calculate the Ln Lp, Lp are much higher than WD, right? So these minority carriers, they don't recombine inside the depletion region, right? We'll come back to this point, right, later, right? But keep in mind your depletion width in most cases is lower than Ln and Lp. And again, as we discussed earlier, your Ln and Lp are functions of doping, right? So if there are, I mean, if you increase your doping, your Ln and Lp will also reduce, right? Because the doping increases, there is more possibility of recombination. So your Ln and Lp will reduce. Okay. So now, if I want to draw this formulable, so based on the concentration, right? Based on the carrier concentration, I could draw the formulable. So EFN, and since the electrons are injected and your minority carriers in the P side of the electrons will reduce also. So I have a EFN in the P side also, right? And I have a gradient of EFN in the P side. Similarly, I have a gradient of EFP in the N side, right? Right. But as I told you, you do not have any recombination and generation in the depletion region. This is the assumption. If you assume that, and if I write down your continuity equation, just let me write down delta Gn by X plus G minus R, and in the depletion region, so this part is 0, and steady state, so I could write that steady state delta Jn by delta X. So Jn is constant, right? So since Jn is constant, right, and we know that this current is electron current is n mu delta EFN by dx, right? So this we have also derived, right? So current is nothing but your quasi-formulable gradient, right? So if Jn is constant in the depletion region, So you could draw the quasi-Fermi levels also constant, right? So basically, df by dx is not changing. df by so uh, okay. So I will come back to this point, right? So okay, let's leave it here. I'll not complicate the things because at this point, just keeping in mind, I'll come back to this point. Keep in mind that your Fermi levels will be constant. Uh, your Fermi levels will be constant in the depletion region, quasi Fermi levels. So if you want to draw the quasi Fermi levels, so your EFN, sorry, your EFN you could draw in the N side, and in the P side also in the, so it will be constant till the age of the depletion region in the P side, and EFP is constant till age of the depletion in the N side, right? Okay. So let's not discuss about this thing right now. We'll come back to this point later because we have to do the derivation anyway, current derivation, right? But do you have any questions till this point?
Hello, sir.
Yeah,
Sir, when we started with the equation that n equals to nc e to power
can you please speak
ec.
loudly, I could not hear properly.
Hello.
Yeah.
Sir, we started with the equation that electrons in the conduction band in the n side is nc e to the power minus ecn minus ef by kt.
Hmm.
But sir, but when we were writing about electrons at minus xp level, that is nc e to the power minus e3 minus ef by kt, right?
Hmm.
So, but my E3 level is same as ECP. So why this NP is just electrons at minus XP? Why it is not for the whole, all the electrons at in my P side
But
conduction
ECP
level?
may be uttai hai na. I mean, I am coming back to this equation. I mean, what I don't understand your thing. But if you see here, right, I have written E3, right, because I could write ECP also here, right? I could also write ECP. E3 is ECP,
Yes, sir.
right? I could write, right? But but the point is, I am interested in the electrons in the p side, so I want to have a equation which will relate the electron in the p side to the electron in the n side, right? If I want to relate to the electron in the n side, I, instead of ECP, I write ECN plus QVBI, right?
Yes, sir.
Right. So that's why in this way, I have just related the n in the, sorry, electron in the p side to the electron in the n side, right?
Sir, I'm just asking like why are we writing it only for minus XP point, not just NP, just
Because
like
this
we
is the
wrote.
this is the point where electrons are injected, right? After this point, those electrons will be recombined, right? So then these minority carriers, see, we are talking about the minority carriers in the p side, right?
Yes, sir.
Right. So minority carriers at this point and this point will not be same. It will only be same if the recombination rate is 0, right?
Yes, sir.
Right. So when I'm injecting right at the depletion region, right? That's what I told, right? When the injection happens from N to P, injection doesn't happen from this side to the here, right? Right. Injection means uh, the electrons from N side are traveling to the P side, right? That is only possible at the edge, right? But the point is, so the number of electrons injected here, right, at the edge of the depletion region, this is how this is the amount of electrons injected, right? But if you take at this point, at some further away from the depletion region, there is a possibility of recombination, right? So the minority carriers, I mean, the electron will not be same, right? So injection, jitna inject hua, that will also go on reducing as you move away from the junction, away from the depletion edge, right?
Yes, sir.
Right. But if I assume in we will have also a case that is the case for the means also in bipolar transistors, right? So when the recombination, there is no recombination, assuming that there is no recombination, right, right. If you assume that recombination, so means the electrons injected, they are not recombining, so it will say, means then they will but they will also reduce, but they will reduce in a different rate. Huh.
Yes, sir.
So when we're talking about injection, because injection is how many electrons are coming from N, right? And the exact amount you could always measure at the edge of the depletion region, right?
Yes, sir. Got it.
Okay. Anybody has any other question?
Sir, can you please once again explain that the bending of the quasi-Fermi levels at the depletion region, like how they are?
Which one?
So the last
Why the
slide.
quasi-Fermi is constant?
Yes, sir. Yes, sir.
Yeah, I mean, as I told, I'll come back to this point later, right? Right.
Yes, sir.
So at this point, because once let me derive the current equation, I'll come back to this point later, right? So at this point, you just assume that EFN is constant in the depletion region, EFN and EFP are constant in the depletion region, right? And this is based on that we are assuming that there is no recombination happening in the depletion region. I will come back to this point later.
Yes, sir.
Okay, so now we'll start deriving the current, right? So the starting point is so we have excess minority electrons at the edge of the depletion. I'm writing it again, right? Edge of the depletion region, right? Because see, the electron injection only happens at the edge, right? So if you go a little bit away from the edge, so injected electrons, there is a possibility of recombination, right? So how much electrons are injected from N to P, the exact amount you could only find at the edge of the depletion region, right? Right. So we have excess minority electrons at the edge of the depletion region, which is x equal to minus xp dash in the p side. So these excess minority electrons will diffuse because there is a concentration gradient. As I told, if you look at this point here and away from the junction, right? So there is a concentration gradient, right? And here we are assuming, in the first case, we are assuming your WP is much more than Ln, right? That means the minority carriers that are injected from N to P are combining inside the P region, right? Right. So your WP is more than Ln. So then the case, then we write the continuity. If you write the continuity equation for electrons, so I could write Nx by del T is always 1 by Q. So because the electrons will move, there is electron current 1 by Q del Gen by day minus Rn plus Gn, right? So this is my continuity equation for electrons. And here you see, I am assuming that there is no generation. Generation will only happen if I have very high electric field, or there is some additional like light falling on the semiconductor, right? So that is not happening. So my Gn equal to 0. So there is no generation of electron hole pair happening, but there is a recombination, right? And I know that I could write I this is nothing but delta n p divided by tau n, and so basically the recombination rate depends on the lifetime of carriers in the lifetime of n-type carriers in the p region, and the excess carriers, right? If the excess carriers will be high, there will be more recombination, right? Okay. So and a couple of assumptions here. We are assuming that there is no recombination in the depletion region. In depletion region, and also we are assuming that this is low level injection, right? So what is low level injection? So low level injection is the electrons that are injecting delta and p, right? So the is less than, right, the doping, right? So this is the, right, so this is the condition. So your low level injection here, the minority carriers in the p side is less than the doping, right? So this is a very important um, assumption here, because uh, so basically what happens, as I told you in the last class also, right? So because if you look at your let me take this, right? So if I look at this region, right, so electrons are injected, but this region here, this highlighted region, this is charge neutral region, right? So this is charge neutral, right? What do you mean charge neutral? So your total charge, which is nothing but you could write that as P minus N plus Nd plus minus Na minus, right? Right. This is zero, right? This is the charge neutral region. Charge neutral region means there is no electric field. When the charge in the, means in the this region there is uh, total charge is zero. That means the electric field will also be zero, right? Okay. So now what I'm doing is, so let's say, uh, so in the equilibrium condition, right, when I'm not injecting electrons, right, so I had Na minus तो नहीं है उधर, क्योंकि this is a p type, sorry, right, okay, so this is n type, p type doping, p type region, so there you don't have Nd plus, right, so donor ions तो नहीं रहेगा, right, p side में, right, so this will not be there, right, so this Nd plus will not be there, so we had only p minus n minus Na minus, and and assuming that your n is much lower, right, so your hole is neutralized by this Na minus, so total charge is zero, right? But now what is happening is, when I'm injecting electrons, so n is increasing, right? In the n in the p side is increasing, right? Let's say at the edge of the depletion region, right? At the edge of the depletion region, you are injecting electrons, you are putting electrons from the n side, right? That means your n in the at the edge is increasing, right? So to maintain quasi neutrality or neutrality, what happens? The majority carrier concentration will also increase, right? So there is a majority carrier response time which is order of picosecond, right? The moment you inject something to maintain the neutrality, your semiconductor will also create a additional number of holes, right? So, so here we are assuming that this injection is low level. That means the delta NP that you are injecting, the electrons that are injecting is much less than Na, so that because delta NP also creates okay, let me write down. So delta NP also creates delta PP, right? Because to maintain charge neutrality, right? This is to maintain charge neutrality, right? And this is a response. This is generated very fast by the carrier, means you call it a relaxation time of semiconductor, right? Because this is in the order of picoseconds, right? So the moment you put some minority carriers, the similar kind of majority carriers will also be generated. That is by this relaxation time. It's very less, right? Instantly your semiconductor will respond, right? So if so, but point is that we are assuming. So your assumption is delta P is less than Na to make sure that your majority carriers is not changed. That means I have already N a number of holes before, right? Right. So the injected carriers is less than number of holes. That means this delta PP doesn't have much impact on the majority carrier concentration, right? So the number of holes will still be Na, because Na is much higher than delta PP, right? Right. So it will be easy, right? You don't have to take care of the majority carrier. The only if there is a majority carrier gradient, let's say if I have a majority carrier, so if I see so I think this part has to be very clear. So let's say this is my depletion region. This is my depletion region, right? And I'm injecting a delta NP here, right? And here also I have some delta PP, right? Right. So if my majority, I do not want a majority carrier gradient, right? So this majority carrier gradient can be avoided in the low level injection condition, right? If there is a majority carrier gradient, we'll have an electric field, right? And that electric field means then we have to consider the drift, right? But low level injection will allow you to only consider diffusion, right? So this low level injection, this assumption only allows to consider diffusion, right? And consider diffusion because there is no majority carrier gradient, right? No majority carrier gradient. Okay, so is this part clear?
Yes, sir.
Okay, okay. Now, um, so if I write, let me take this. Yeah. Okay, so in the steady state, I could write this 1 by q and del by dx. So there is no, so I could write a q dn delta np x by delta x. This is uh, by only, I am considering only diffusion, right? Only diffusion. Right? So then my equation becomes dn del square by del x square delta npx minus delta np tau n equal 0, and I could also write this as delta npx ln square because your dn tau n root of dn tau n is ln, right? This we had earlier derived, right? So this is my equation, right? So assuming that there is no high level injection, so we only have to take care of the diffusion, and I could write down this equation. So this equation I have to solve to find how this delta npx is changing. So the solution of this nx is, I could write down as a to the minus x times ln plus b e to the x by ln, right? So this is the solution of this differential equation, right? So this is how your excess magnetic errors vary in the p side, right? Right, right. So then I have to put the boundary condition. So to so I know couple of things. Delta np at minus xp, I know this is ni square by na e to the power q applied voltage by kt minus 1. That but I know, right? And I know that delta np at infinite or minus infinite is 0, right? So so if I so basically because assuming wp is much higher than ln, right? So I could also assume that, right? Okay, so for this case here, right? So so this is condition 1, this is condition 2. So this applying this boundary condition 2, right? So right, so which one will be 0? A will be 0 or B will be 0? So this is 0.
B.
Which one will be 0?
A. A will be G.
So A will be e to the alpha. right? So basically A will be 0, right? Right. So your delta NPX will be B e to the power x by ln, right? And again assuming delta NP minus XP is B to the power e to the minus XP by ln. So B equal to this equal to Ni square by Na e to the power QB by Kt minus 1. So B will be Ni square by Na e to the power QB Kt minus 1 times e to the power xp, right? So this will be my B here, right? Then I could write down my equation. My delta NPX is B e to the power x by ln, and B is so it will be Ni square by Na e to the power q by kt minus 1 e to the power x plus xp, right? Okay, so this is how your delta NP will change. So you could see at x equal to minus xp, so your delta NP will be Ni square by Na times e to the cube here by kt, and if you go far away from the edge of the depletion region, your delta NP will become 0, right? Right. So this is delta NPX. Similarly, I could write also delta PNX, right? Because I am also injecting, Okay, okay. So I could also write delta PNX. I also injecting electrons from p side to n side. So this will be QBF by KT minus 1. So this will be I think it will be Xn minus X. Right. So I mean, so you could do that. Sorry, you could do that. Means solve this equation also, right? Okay. So um, so basically now I have basically I have find out this delta NPX and delta PNX. So let me. So this is nothing but this is what we had drawn here, right? Right. This is how your excess minority carriers vary, right? And this is so basically you see this part here, right? This part, right? So this part is governed by this equation here, right? So the exponentially changing the minority carrier concentration, and this part here is governed by this equation, right? Uh, okay. So we are already 1 minute past 12. So let me stop here. And since now, so now we know how the minority carriers vary with X, right? So once we know that, then you could find the current, because current is nothing but uh, uh, it could also write down. So your current is nothing but Q times for an electron current. This is delta by del X, delta NPX, and my whole current is nothing but QDP, delta by del X, delta PNX, right? So since I know NPX and PNX, how they change with X, then I could easily find the JN minus JP, right? Electron and hole currents, right? That will derive in the next class. Okay, so let me stop here, but we could discuss if you have any questions.